Good morning. We start with a new chapter, Mechanical Properties of Fluids. And this chapter we start by discussing the variation of pressure with depth in a fluid. So I've drawn something here. This is a cylinder that's containing a liquid, and the liquid has a density rho. And you will see that inside the liquid we are considering a fluid element. So this could be a fluid, it could be gas or a liquid, which is what we call as a fluid. So I have considered a fluid element, and because this fluid is at rest, we should know that in this fluid element would mean a small cylindrical part of this fluid inside that container of fluid which is already at rest. And so because the fluid is at rest, this element also should be at rest, which means the vertical forces must balance each other, and the horizontal forces also must balance each other. Now if you look at this fluid element, we know that its weight mg will act in the downward direction, and the fluid above will exert a pressure in the downward direction here, and the fluid below will exert an upward pressure, which I call as P2 here. This fluid element has a area, cross-sectional area A and height h. So now I'm going to, because this fluid element, the whole fluid is at rest, we know that the downward forces must be equal to the upward forces. So I'm going to equate the forces acting in the downward direction is 1, the weight of that element in the downward direction, plus the force due to that pressure exerted by the fluid on top. Now as you know, force is equal to pressure into area, because pressure is force by area. So I may write this as plus the downward force is going to be F1 into A, P1 into A, which must be equal to the upward force, that is P2 into A. Now I may write, bringing this to the right hand side, P2 minus P1 into A is equal to M into G. This area, now this mass, as you know, is volume into density, because density is mass by volume. Volume of the cylindrical element is base area into the height into rho. So I'm going to substitute for mass here as AH rho. So I may write P2 minus P1 into A is A into H into rho G. If I cancel this, we see P2 minus P1 equal to H rho G, where H is the height of that liquid column or liquid element or fluid element we have taken. Rho is the density of the fluid, and G is acceleration due to gravity. Now imagine this fluid element is on the surface of this liquid. If it's on the surface, it means that this P1 is open to atmosphere. So you may equate the P1 to atmospheric pressure, PA, and let us equate this P2 to some pressure P, which is at a depth h from the surface of the fluid. So this equation will now become, instead of P2, I'll replace it with P, which is the pressure at some depth below the surface of the fluid, minus PA, because P1 I said it is at the surface of the fluid, so it is open to atmospheric pressure. This is equal to H rho G, and this is what you call as the gauge pressure. Gauge pressure, the atmospheric pressure being PA. So we have H rho G being the pressure at some depth h from the surface of the fluid, rho being the density of fluid. Okay, now here atmospheric pressure is the pressure exerted by, so at some point, let's say at some point we need to know the atmospheric pressure. So atmospheric pressure would be, suppose you take a cylindrical column of air, you want to find the pressure at some point P, atmospheric pressure. If you till the top of the atmosphere, you take a cylindrical column whose base area is 1 meter square. Then the weight of this air column, that is mg, for unit area of cross section, that weight exerted at this point will be called as the atmospheric pressure, and at sea level this atmospheric pressure PA is equal to 188, or this is equal to 1.013 into 10 raised to 5 Pascal, Pascal being the SI unit of pressure. Now we have something called as the hydrostatic paradox, which I have drawn here for you. This hydrostatic paradox shows you we have the same fluid in all the three vessels. So obviously the rho is the same, the density is the same because it's all the same. And you will see that these containers are all of different shapes. But if you take the pressure at 3 points, A, B and C, which is at the same depth from the fluid surface, you will see that the pressure at all these points, PA, must be equal to PB, must be equal to PC, because PA is H rho G, which is the same in all the three cases because rho is the same since it has the same fluid, continuous fluid. So the pressure at this point ABC simply depends on the height of the fluid column above that point. So this is what is called as hydrostatic paradox, because even though this vessel and this vessel and this vessel contains different amounts of liquids above that points, the pressure exerted will be the same, showing you that the pressure exerted at some depth below the surface of fluid depends not on the shape of the container, not on the amount of fluid above it, not about the base area or anything. It depends only on the depth at which you are considering the pressure point. And if they are at the same depth in the same liquid, then all points will have the same pressure. We now move into Pascal's law. Pascal's law, which states that if you apply an external pressure to any part of a fluid contained inside a vessel, it is transmitted equally and undiminished to all parts of that fluid. Like, for example, suppose we have a, let's say, a container like this, and I have fitted it with a piston. Let's say this is full of air. Okay. Now, if I push this down with some force F1, which is equal to F equal to PA, pressure into area. Now, this pressure, which is F by A, will be transmitted because this is a fluid contained, air fluid contained inside a vessel. This pressure that you exert here will be transmitted equally and undiminished to all parts of that fluid. Everywhere it will be exerting equal pressure, and this is what Pascal's law states. That is, if you apply an external pressure at any point of the fluid, it is transmitted undiminished and equally in all directions in that fluid contained inside the vessel. So pressure is F by A, which is, as you know, Newton per meter square. There's a unit, and that's also what you know as Pascal. Two major applications of this Pascal's law that you have to learn is, one is hydraulic lift. So that's what we're going to discuss now, the hydraulic lift, which you must have seen in the car wash areas, in your petrol pumps and all, where they lift the car while they want to do some maintenance or wash the car. We have a hydraulic lift that lifts up the car. This hydraulic lift has two cylinders like this here, and there's a fluid here, either air or any kind of fluid, and we have a piston here whose let's say this is area A2. We have another piston here whose area is A1. Now, if I apply a force here, F1, which is P1 is equal to F1 by A1, because this is a smaller piston. But according to Pascal's law, this pressure that I exert at this point will be transmitted equally and undiminished to all parts of the fluid, which means this is also going to experience a force F2, which is going to be the pressure exerted here, P2, and this is P1. P2 is equal to F2 by A2. Now, by Pascal's law, P1 and P2 are equal. So, we may write F1 by A1 is equal to F2 by A2, or I may rewrite this as the force F2 is now equal to A2 by A1 into F1, which means this, if this A2 by A1 is large, for example, let's say this is 100 centimeters square and this is just 2 centimeters square, roughly. So you will see a 50 times increase in the force here, because A2 by A2 is larger than A1. So even if you apply, let's say 1 Newton force here, you will see A2 by A1 ratio is 50. So you will see a 50 times increase in the force that is applied here. So this A2 by A1 is what you call as the mechanical advantage, because that's the factor by which this force is multiplied when it comes to the second piston of larger area. So this is what we have in hydraulic lift. So you have to apply a very small force here. It will be multiplied A2 by A1 times when it comes to the larger piston of larger area, and so you can keep a heavy load and raise it up easily by applying a small force here. That is hydraulic lift. Hydraulic brake is also another application of this Pascal's law. And in hydraulic brakes, this is a very rough diagram that I have drawn here. You have your pedal here where you apply the brakes. This is now connected to something called as the master cylinder, and this master cylinder is connected to a wheel cylinder, and the wheel cylinder is then connected to the brake shoe, and this then touches the wheels. So this has what you call as the brake fluid. So when you apply pressure on the brake, this pressure that is applied here, that is, let's say this has A1, and this one's area of cross section here is A2, this piston. So when you apply a pressure here, which is P1, which is equal to P1, which is equal to F1 by A1, the same pressure is transmitted through the fluid to these pistons which are of area A2. So the pressure here will be P2, which is F2 by A2. Like in the previous case, Pascal's law says P1 should be equal to P2, or F1 by A1 equal to F2 by A2, which tells us that F2 is equal to A2 by A1 into F1. So that means when the wheel cylinder has area, the pistons have larger area, A2. So this mechanical advantage is A2 by A1. So because this is larger, A2 by A1 will be a large number, multiplied by whatever force you are applying here. You are applying with your foot some force F1, will be multiplied A2 by A1 F2 times, and that will be transmitted to that pressure, or that force will be transmitted to the brake shoe, which will now push against the wheels, and that's how you can stop the tires because of this expansion. And then after that, this spring will bring it back to its original condition. So this is how Pascal's law is applied to both hydraulic lifts and hydraulic brakes. The next thing we move on to will be the fluid dynamics, because so far we have been discussing about fluids at rest. We now move into fluid dynamics, that is, we discuss about fluids in motion. We start with the two types of flow. Fluid flow can either be steady, which is also called laminar flow, or it could be turbulent flow. So let's consider the path of a fluid particle like this, okay? A fluid particle moving in this path. I'm going to consider a point A, another point B, and another point, let's say C. If I draw a tangent here, this represents the fluid velocity at point A, this represents the fluid velocity at point B, and this represents the fluid velocity at point C. Now, the fluid flow is said to be steady or laminar if every fluid particle that reaches A maintains the same velocity, and as it moves on to B, every fluid particle must maintain the same velocity as the previous particle, and as the first particle reaches point C, if it has a velocity Vc, every particle that comes after it must maintain the same velocity Vc when it reaches point C. It does not mean that A, B, C should all have the same velocities. The fluid particle may change its velocity from Va to Vb to Vc and so on. Steady flow only means that every particle that reaches A must maintain the same velocity Va at any point of time. Similarly, every particle that reaches B must maintain the same velocity Vb, and as it proceeds to C, every fluid particle must maintain the same velocity Vc. So this kind of flow is what you call as steady flow or laminar flow, and also the path taken by a fluid particle which is in steady flow, it is what you call as the streamline. So the trajectory or the path that a fluid particle takes when it is in steady flow is what you call as streamline, and two streamlines cannot cross each other if the fluid is in steady flow or laminar flow. So you can't have two trajectories crossing each other, because if they do, then it means that at that same point you can have two tangents, which means the same fluid particle can have two fluid directions, which is not possible when you're talking about steady flow. Steady flow is possible when the flow speeds are very low speeds. If the velocity of the fluid particle or the velocity of flow of a fluid goes beyond a limiting value, which is called as the critical velocity, then the fluid loses its steadiness and the flow becomes turbulent. Turbulent flow is defined when the fluid particles, when they reach a particular point, for example, in our point here, A, when a fluid particle reaches point A, the fluid velocity does not remain a constant in time, meaning the first particle that reaches A may have a velocity Va, but the next particle that comes to point A need not maintain the same velocity. So every fluid particle that reaches A can have different velocities. In that case, you call such a flow as turbulent flow. Reynolds defined a number called as the Reynolds number, which gives us an idea about whether the liquid flow is steady or turbulent. The number is given by Reynolds number rho v d by eta, where rho is the density of the fluid in consideration, v is the velocity of the fluid, d is the dimension of the container or the dimension of that pipe through which we are considering the fluid flow, and eta is the viscosity of the fluid. Viscosity we will be discussing in the coming session. So depending on all these factors, he gave a number called as the Reynolds number, which will give us an idea about whether this flow is steady or turbulent. If this Reynolds number is less than 1000, then the fluid flow is steady. If it is between 1000 and 2000, that is 1000 less than this number, less than 2000, then the fluid flow is unsteady, could become steady or could become turbulent. But if this number Re is greater than 2000, then surely the fluid flow is turbulent. So this is how Reynolds defined a Reynolds number depending on the factors rho, v, d and eta, which will tell us whether the flow is steady or turbulent. So this is all we have to discuss in our first session, and we'll continue in our next session. Thank you.